Hi everyone, so this is my project which is AMIHAN, a station-level air quality risk profiling based in Spain, where we explore the impact of urban design and traffic on air quality risk. So first, let me introduce myself. My name is Julian Reyes, and I'm an undergraduate studying data science at Mapua University. So, in my project for Altair's Global Student Contest titled AMIHAN, I aim to shift the focus from general air quality predictions to identifying which urban PM10 monitoring stations in Spain are at structural risk, along with the underlying reasons for this risk. So let's tackle my data scope. First, my source is from the Altair Contest air quality metadata. And then I applied filters that focus on Spain, urban areas, and stations that monitor PM10 levels. And then the final dataset subset, which is 425 records or rows of the filtered data, which is a solid foundation for risk profiling given that there are a lot of columns as well. So what is my rationale for my target? First, there is no direct PM10 concentrations within the dataset, so the dataset lacks direct measurements of PM10 concentration, hence alternative calculations based on emissions, location, etc. So then we have the proxy risk label definition, which is a dual class risk label that was created where traffic related stations are identified as high risk, which is 1, while other urban stations are classified as low risk, which is 0. So, this classification framework transforms the problem into a two-class classification challenge, identifying whether a station falls into the high traffic dominated risk category or not. So, what are the features that I used? First, we have the key location attributes. Second is the emissions and traffic data. Third are geometric context factors. And fourth is air quality station characteristics. The modeling approach is then started with the filtering process. So, like I said earlier, we apply specific filters to prepare the subset targeting Spain and PM10 pollutant and urban areas. And then we created the risk labels such as 0 versus 1, which is low risk versus high risk urban stations. And then the feature selection for modeling, we used attribute selection to improve model accuracy, and any features related to emissions, traffic, geometry were identified to affect and inform the risk classification. So, during the model selection, multiple algorithms were assessed to determine the best fit for classifying PM10 risk levels. So, there were a total of 9 number of models evaluated, but the final model was a decision tree. So, how did the model perform? First of all, we have a 70.2% accuracy, a 0.77 AUC, a 0.75 precision, 0.75 recall/sensitivity, and a 0.63 specificity. So the decision tree classifier demonstrates reasonable performance metrics, achieving a balance between accuracy and interpretability for a metadata-only dataset. The key drivers in this case, the feature importance. What are the features that affected the predictive model the most? So first is the street width, which is 0.237. So street width emerges as the most significant factor influencing the risk classification of PM10 monitoring stations. Narrow streets tend to trap more emissions, increasing the likelihood that a station will fall into the high risk category. So the second one is traffic volume, which returned a 0.079 score, which indicates that higher volumes of traffic are associated with an increased risk classification. This suggests that monitoring stations located on busier streets are more likely to be at risk due to elevated pollutant levels. And then the third one is distance source, which is 0.059. This metric reflects the proximity of monitoring stations to significant emission sources. Closer distances to these sources correlate with higher risk classifications for PM10 monitoring stations. Fourth one is the main emission sources, which is a categorical variable. It returned a 0.051 score, which helped confirm the type of emissions impacting specific stations. So it indicates that the dominant emission source, particularly road transport, plays a significant role in defining the risk level of a station. Okay, so now we have the interpretation and insights. So let's understand the risk factors. So the model effectively correlates urban geometry such as street width and traffic intensity with the risk levels of PM10 monitoring stations. Understanding these relationships is crucial for urban planning and public health strategies. And then second one is we have the predicted risk classification. By categorizing each station into predicted risk classes, the model provides a clear distinction between high risk, which is 1, and low risk, which is 0, stations. This classification aids in prioritizing areas for intervention and monitoring. So, what is the unique value and impact of AMIHAN? So, AMIHAN provides a detailed analysis of urban PM10 monitoring stations, moving beyond basic air quality indices or AQIs. By using Altair AI Studio, the project not only identifies high risk stations but also elucidates the specific traffic and geometric factors contributing to that risk. So, we empower the city planners with actionable insights for strategic interventions and very easy methods in order to do that. And that is AMIHAN, which is a station level air quality risk profiling based in Spain, where we explore the impact of urban design and traffic on air quality risk. Again, I am Julian Reyes, a BS Data Science undergraduate in Mapua University. Thank you for listening.